Well, hi, welcome back. This is our second lesson on probability. We're going to talk about something called conditional probability. So today you're going to calculate conditional probabilities for dependent events. So first let's look at what is conditional probability. What do we mean by that? So if two events are dependent, meaning that they affect each other, we have to take into account the changes in the probability of one event caused by the occurrence of the other event. So to denote a conditional probability, when we use that probability notation, it looks something like this. So we have a P of A, and then there's this line, this kind of vertical line that represents given, and then B. So that means the probability of A given B. So before we get into some examples, we're going to talk a little bit more about what that given actually means. So one way to think of the given is look for situations in which the question you're asking narrows down your total. So let me show you what I mean. So if I were to ask the question, what's the probability that a randomly chosen student at McNeil knows how to drive? So we might think, okay, there's, 16 years old is when you learn how to drive. 16 usually happens when you're a junior, maybe a little bit before that. Not everyone learns how to drive right when they're 16. So we can probably assume that somewhere around half, maybe a little bit less, maybe a little bit more of students know how to drive, right? So we're talking about all McNeil students who know how to drive. But if I change that question to say, what's the probability that a randomly chosen senior at McNeil knows how to drive? Well, that's narrowing things down. So the given here would be that they're a senior. So we would ask this as, what's the probability that they know how to drive given that they're a senior? And that changes things, right? Because seniors are all going to be in that 17 to 18 range, which means that they very likely already know how to drive at that age. Whereas if I had said, what's the probability that a student knows how to drive given that they're a freshman, it's going to be a little bit different of a story. So that given is narrowing down your total from the entire group to now just a specific subset of that group. So let's look at an example. We'll talk about the student drivers since that's what I just gave an example for. So suppose that at a high school there are 625 seniors. There are total 1,123 students who drive, and there are 498 who are seniors and who drive, so they're both. There are 2,620 total students at the school. So what I'm going to do here is draw what we call a Venn diagram. This just can help us organize information that we have in a way that's a little bit more helpful for us in terms of probability questions. So I'm going to start by drawing a circle that represents seniors. And I just put in parentheses underneath the word seniors how many total seniors there are so that I don't forget. Now I'm going to draw another circle that represents the number of drivers. And again, I put the total number of drivers in little parentheses underneath that word. We also know that there are 498 students who are both seniors and drivers. So they're in that overlap section that accounts for both. And if you remember what I talked about when we did some two-way tables last class, those 498 students are counted in the seniors total, and they're also counted in the drivers total, right? So that's kind of why they're in that overlap. So if I wanted to answer the question, what is the probability that a student drives? So just overall, out of all the students, what's the probability that they drive? So I could say probability of driver, say there's total, the number of drivers divided by the total number of students, right? That's that part over whole that we've talked about before. So there are 1,123 drivers out of 2,620 students total, which comes out to about 0.43. So that's out of everybody. What's the probability that a student drives? But then on part B, what is the probability that a senior drives? Well, that's a little bit different because now I'm not necessarily talking about the entire group of students. I'm only asking about seniors. The way I denote that in notation is like something like this. Probability that they're a driver given that they're a senior. Sometimes the way we see it in notation, it feels kind of backwards, but that's just because whatever's the given thing always comes after that line. So the way I could look at my Venn diagram to figure this out is because I'm only talking about seniors, I'm just going to kind of ignore the driver's circle, and I'm really only looking at the seniors circle. So that seniors, the total number of seniors, is now going to be my denominator because that's the total group that I'm dealing with. So I'm going to put the 625 on the bottom. So on the top is supposed to be the number of drivers in that group of seniors. So if I look at the way I have my Venn diagram, I can see that in terms of drivers, well, that's going to be this overlap section. Those 498 were the ones that were also in the driver circle because they were also drivers. So in that circle of 625 seniors, we know that 498 of them know how to drive. So that becomes the top part of my fraction, which when we divide that is 0.64. Let's do another example very similar to that just to practice it one more time, and I'll go through it a little bit quicker. Professor Jackson is in charge of a program to prepare students or people for a high school equivalency exam, like the GED. Of the 150 students in the program, 120 of them need work in math, 105 of them need work in English, and 83 need work in both. So again, I'm going to draw one circle that represents the students who need help in math. There's 120 of them. One circle that represents the students who need help in English. There are 105 of them. And then I'll go ahead and put that 83 in the overlap area that represents both. So if I wanted to know what's the probability that a student needs help in English, so probability of English, there are total 105 who need help in English out of 150 students total, which is 0.7. And then what's the probability that a student who needs help in math also needs help in English? So this is asking it a little bit of a different way, but when we say that a student who needs help in math, that's our given. We're now narrowing down our total to only look at the students who need help in math. So the way I write that is what's the probability that they need help in English given that they need help in math? And again, we can kind of ignore the English circle since it's given that they need help in math. We're only looking at the math circle. I know that the total number of math students is going to go on the bottom, so 120. And then in that circle of math students, we know that 83 of them also needed help in English because they were in that overlap section. And when I divide that, I get 0.69. So let's look at an example with a Venn diagram answering the same sorts of questions, but with a two-way table, not with a Venn diagram. So this is going back to an example from the last lesson because, cats and dogs, very important. So Ms. Sorensen would survey her class about whether they like cats and dogs. The results are shown in the table. It's the same table from the last lesson. So if I wanted to know what's the probability that a student likes dogs, that's out of everybody, any student. We're talking about the entire group. So probability of likes dogs, there are 20 total students who liked dogs out of 25 total. That comes out to 0.8. And then what is the probability the student who likes cats also likes dogs? So just like on that last example, saying that a student who likes cats, that's kind of our given because we're saying we already know that the student likes cats. We want to know what's the probability that they like dogs as well. So that becomes our given. So again, the way we would write that, what's the probability that they like dogs given that they like cats? And how that works on my table, when it's given that they like cats, that means I only really care about this one column right here of students who like cats. I'm going to pretty much ignore the rest of the numbers because I'm only dealing with students who like cats. So in that column, there are 16 students total who liked cats. And in that column, 15 of them also liked dogs. So 15 out of 16, which is 0.94. So part A, what's the probability that any student likes dogs is 0.8. But given that they like cats, they're much more likely to also like dogs. So we can kind of see that difference. Let's do another one of those with the two-way table. At Hopewell Electronics, all 140 employees were asked about their political affiliation. The employees were grouped by type of work as executives or production workers. We have the results in our lovely little table. So executive, production worker, and then we have if they're Democrat, Republican, or independent. So what's the probability that a randomly chosen employee is a Republican? So just out of everybody, out of all the employees, Nothing's given. We're not narrowing down our total at all. We're just talking about everybody. So probability of Republican, there are total 55 Republicans out of 170 people total. Although I just realized that up here says 140 and that says 170. Hold on, we're gonna do some math checking. Okay, I fixed it, it's 140. So I just had to double check and change that. Sorry about that. So 55 out of 140. So 55 students or people who are Republicans out of 140 total gives me about 0.39. So that's the total overall probability that someone's a Republican. And then part B, what's the probability that an executive is a Republican? So again, I'm narrowing down my total. I'm no longer talking about all of the employees. I'm talking about specifically the executives. So the way I would write that is a probability that they're Republican given that they're an executive. And then the way that I would look at that on my table is I'm only looking at that top row of executives because that was my given, that was my narrowing down of the total. So in that top row, I can see that 34 are Republicans out of 48 total. So 48 was the total number of executives because that was given. And then in that row, 34 were Republicans and 34 out of 48 is 0.71. So that is another example with a two-way table and how we can look at that and find those conditional or given probabilities. Another situation in which conditional probability is used, even if we don't necessarily think of it as like given or conditional in the normal sense, is when we are choosing items or people or whatever without replacement. We actually did an example like this in the last lesson, but just to reiterate it and kind of look at it more as a given probability. It's the same as Calvin, that's me. Sixth period class has 7 juniors and 20 seniors. If she chooses 2 students at random, so we're choosing 2 students, what is the probability of that? So if I'm choosing 2 students, it's kind of implied that I want 2 different students. So I'm choosing students without replacement. I'm going to choose one, and then of the remaining, I'm going to choose another. So because of that, there's going to be a little bit of a change or a dependency between the probability on the first and the probability on the second pick of a student because we have less people in the class and less of that particular grade level. So if I wanted to know what's the probability that both students will be juniors. So I want a junior and another junior. So we think back to last class, that and probability, we multiply, right? And that's what we're doing, but we do have to kind of consider how the probability changes after I pick the first student. So that's the conditional part of it. I'm making that change based on what happened previously. So the first time I pick a student, probability that they're a junior, well, there's 7 juniors out of 27 students total. Then I'm going to multiply, because that's what we do for and. And the second time I pick a student, and I still want them to be a junior, assuming, given that I've already picked a junior before, there are now only going to be 6 juniors, and there are only going to be 26 students total. So we're making that adjustment based on what happened before. That's what makes it conditional. I multiply the top, multiply the bottom, and then divide and get my answer. My probability that both students will be seniors, similar option, right? Senior and senior. So the first time, there's 20 seniors out of 27 total. The second pick, after I've already picked a senior once, there's 19 seniors out of 26 total. Multiply the top, multiply the bottom, there's my answer. Part C, probability that the first student's a junior and the second student's a senior. Well, the first time I pick a student, probability of getting a junior would be 7 out of 27. There's 7 juniors, 27 total. And the second pick, I want a senior this time, given that I've already picked a junior. Well, there's still going to be 20 seniors, but now there's only going to be 26 students total. Multiply the top, multiply the bottom, and there is my answer. So we can kind of see that conditional probability work out in a situation like this, even though we may not think of it in the same sense as we did on those other problems. So the and rule revisited, right? We talked about, we multiply them before. In the last class I said, as long as A and B are independent, we can just multiply probability of A times probability of B to get the and. So now I'm going to kind of revisit that and give you a little bit more detail now that we've talked a little bit about that given or conditional probability. So the probability of 2 or more events occurring is probability or product of the probability of the first event and the probability of the second event given that the first has just happened. So in other words, our actual formula for and is we do the probability of the first thing times the probability of the second thing given that the first just happened. So when we have that dependent situation where our first event is affecting the second event, we have to make that adjustment, just like we just saw on the last example with the juniors and seniors. I had to make that adjustment by changing the fraction a little bit on that second pick. And that's how we kind of actually do an and probability. We have to take into account that change in probability. So just to put that through one more example, testing cameras, a quality control procedure for testing digital cameras at a factory consists of drawing 2 cameras at random from each lot of 100. If both cameras are defective, then the entire lot is rejected. So part A, if a lot of 100 cameras, so a group of 100 cameras has 10 defective cameras, what's the probability that we will draw 2 defective cameras in a row? So 10 of them are defective. We want to know if I were to pick randomly, what's the probability that I get 2 defective cameras in a row? So I want a defective camera and another defective camera. The first time I pick, there's 10 defective cameras out of 100 total. Second time I pick, there's only going to be 9 defective cameras because I already picked one out of 99 total. Multiply the top, multiply the bottom. It gives me about a 0.009 chance of getting 2 defective cameras in a row, which is not very likely. So if there's only 10 defective cameras in the lot, it's not very likely that we'll reject the entire lot by picking 2 defective cameras in a row. Part B, if the lot of 100 cameras has 30 defective cameras, what's the probability that we get 2 in a row that are defective? So same question, but now there's 30 out of 100 defective cameras on the first pick. And then the second time I pick, there would be 29 defective out of 99 total. And that comes out to 870 over 9900, which is 0.088. Still not a huge chance, but it's definitely a lot bigger of a chance. It's like about 9% chance, whereas this is less than 1% chance. So we've definitely grown a lot in the probability of picking 2 defective cameras in a row, which would mean that we reject the entire lot. So, all right, that is it for this lesson. Thank you for your attention and have a good rest of your day.